Previously, we explored how transformers handle steady and variable loads. Now it's time to discuss what happens in sudden instant conditions, transient processes. What exactly occurs when a transformer is switched on? Why do such enormous currents appear at that moment, and is there a way to avoid them? A transient process is a brief, non-steady state condition that arises when the system abruptly changes, such as during switching on, switching off, or a short circuit. The most important transient for a transformer is energization, switching on under voltage. At that moment, the magnetic flux in the core has not yet stabilized, and current surges with high amplitude. This condition may last from a few milliseconds to several seconds, but its impact can be significant. Think of it like releasing a pendulum from the top. It accelerates rapidly downward. That's how a transformer behaves when powered up. It receives a strong impulse. Where does inrush current come from? When the transformer is switched on, the magnetic core has no flux, but voltage is instantly applied to the windings. This creates an electromotive force that tries to magnetize the core. If the switching moment coincides with the peak of the voltage sine wave, the magnetic flux doubles, and the current may spike 5 to 10 times above the rated value. A useful analogy: imagine pushing a swing at its maximum height. The added force causes it to swing far beyond its usual path. Factors influencing inrush current include residual magnetization in the core, the switching angle, the phase of voltage at the moment of energization, core design, its cross-section and the type of steel, and network voltage and stiffness. Typical inrush characteristics: amplitude, 5 to 12 times nominal current. Duration, from 0.1 to 2 seconds. In high-power transformers, inrush current can reach 20 to 30 kiloamperes. This requires precise control and carefully designed switching schemes. What problems do inrush currents cause? Protection systems may trip unnecessarily. Contacts in circuit breakers may overheat. Insulation stress increases, especially with frequent energization. And the network may experience voltage fluctuations. This is similar to hydraulic shock when you suddenly start a water pump in an empty pipeline. In electrical systems, the equivalent is an electromagnetic shock. The stiffer the network, the higher the inrush current. This is especially critical in isolated segments, such as power plants. Residual magnetization plays a key role. The core can retain magnetic flux even after the transformer is disconnected. If the next energization applies voltage in the same direction, the flux values add up, causing a maximum possible current spike. To prevent this, engineers use a delay before re-energization, demagnetization, or controlled phase switching schemes. Let's look at a real case. A 250 megavolt ampere transformer is switched on at a substation. An inrush current of 9 times the nominal value lasts for 0.5 seconds. When it's switched on again just 30 seconds later, the inrush rises to 11 times nominal. Why? The residual flux in the core hadn't dissipated. That's why delayed switching or demagnetization is essential. Now a task for you. You have a 100 megavolt ampere transformer being energized at 110 kilovolts. Its rated current is 525 amperes. What level of inrush current can you expect? And what steps can you take to reduce it? Think it over and write down your answers. In the next module, we'll discuss protection and damping methods. Today you've learned what a transient process is during transformer energization, why inrush current occurs and what it depends on, and what risks are posed by even a short but powerful current surge. The analogies we used, a pendulum, a swing, a water pump, will help you visualize these phenomena more clearly. In the next module, we'll explore damping techniques, switching schemes, protection strategies, and how to simulate transients. You'll see more real-life calculations and practical examples.